Okay, our next clip is about the biosphere, everything that involves DNA. This won't be very long because I'm sure you're thinking, what does that have to do with weather and climate? And I'll try and give you an idea as we're on our way through. We can split this into two pieces. The first piece is about marine life, namely the animals and the plants in the oceans. Okay? Now, if you think about sunlight coming down to the ocean, it doesn't get very far. All right, it may already be time for yet another diagram. So here is the surface of the ocean. Here you are swimming quite happily, and in comes some sunlight. And as you probably know, it just doesn't get very far down in the ocean. Depends on a lot of factors. But it doesn't get that far down. So there's a lot of marine life that needs sunlight that lives at the top of the ocean, and this is called the euphotic zone. E-U-P-H-O-T-I-C, the euphotic zone. Okay, that's the depth of the ocean to which light can penetrate, and therefore in which photosynthesis can proceed to keep plant life going. There's a ton of life in the upper part of the ocean, not just fishies, but plant life as well. And all of that life can exist provided that there are nutrients present. It's just like on the surface. As long as there's something to eat, you can have life. And there's a figure in the book that tells us about where these areas are. We've already seen this idea of upwelling before. Upwelling takes place along the western edges of the continents, for example off the California coast, and brings up cold water from the depths, but it's also nutrient rich, and so there's a lot of life in those regions. And we all know along the California coast we have a lot of upwelling because it's cold. That's not the only reason, but it's a big clue. It's cold. Moving on, we have this region full of plants and fish at the euphotic zone. So let's get some animals going in here. Well, let's just say we've got flocks and flocks of fish. I'm not a very good fish drawer, but let's have a school of fish here. And the thing is that when they die, they sink to the bottom of the ocean. So that at the bottom of the ocean, you're going to have, now what does a dead fish look like? I think it looks like this, right? So at the bottom of the ocean, you're going to have a pile of dead fish and dead other plant life. And it turns out that this process takes nutrients back down to the lower part of the ocean. So remember that we had upwelling. It could be time for a new color here. Let's have some blue upwelling. So this is cold, nutrient rich water upwelling to the upper ocean, and then when the fish and plant life die, everything sinks back down again. This is part of a cycle. Okay, this is actually part of the carbon cycle. Carbon cycle we're going to get to talk about fairly soon. When I say see below here, that's a euphemism. It might not be the next slide, it might not be the next clip, but it'll be fairly soon that we're going to get to talk about the carbon cycle. So this cycling of nutrients in the atmosphere is the part of the carbon cycle. Let's have a look at figure 2.10 in the book, because it tells us about regions of the planet, or at least the oceans, where there's a lot of biological activity. I don't know why the pen is so slow. It's kind of interesting though. And it shows us also that there are things called biological deserts in the oceans. This is the version of figure 2.10 that I have. It's not quite the same as in the book, which is interesting. But anyway, it's color-coded as usual. And the important thing is that these purple regions through the central southern Pacific Ocean and to a lesser extent the central northern Pacific Ocean, those regions are biological deserts. There's very little plant life or fish life in the upper ocean here. By comparison, the equatorial ocean, this region here, and along the margin of South America and along the margin of North America, those are fairly rich zones. Even up here you can see along the southern coast of Alaska, it's a very rich life zone. That's interesting that there are biological deserts in the oceans, regions where there's less life and more life. All right. Oh, I guess I should go back and talk about El Nino. El Nino starts out in this region over here off the coast of South America. Normally there's a lot of upwelling and it's a very nutrient-rich area. During El Nino, the upwelling stops and this becomes more of a biological desert. It has a lot of impact on the local fishing economy and so forth. All right, now let's talk about the biosphere on the planet. And a term that we want to introduce here is the term biome. A biome is a region or an area with a given climate that can support a given combination of animal life and plant life, and obviously they tend to go together. Figure 219. Let's see what does that look like. Here we go, figure 219. It's kind of a teeny weeny figure. It's very difficult to see anything, although I can enlarge it a bit. If you want, I can do the opposite and make it incredibly tiny, and then we'd need a telescope to figure anything out. But anyway, all right, so the different colors represent the different biomes here, and I've mentioned a couple that you can keep an eye open for. One is the deserts, which are shaded in gray. So obviously if we look at North Africa, the Sahara Desert, this is a vast area of a certain kind of climate and an absence of plant life. As you all know, it's all sandy and rocky. It is not cloudy very much. It's sunny a lot. It doesn't rain very much. So basically it's hot and dry. Nothing much grows there. So we could call that a biome if we want. The other biome you might want to look for are croplands, which I think are in yellow. If we look at North America, across the Canadian prairies here and across the upper Midwest, those are croplands. So we have this concept of biome, an area of a certain combination of rainfall and temperature, which allows a certain kinds of plants to grow, which allows certain kinds of animals to live. And I've got a little list here of the factors that go into creating a biome. The first one we might think about is latitude. Latitude matters because of something called insolation. It's not the same as insulation, it's insolation. Insolation refers to incoming sunlight. That's something we'll be looking at more in some later chapters. We could think about the resulting average temperature. You're going to have a very different biome if the temperature is above freezing versus if the temperature is below freezing. Let's go back and look at the biomes again. So, for example, up here in northern Canada, in that region, whoa, did not mean to do that. Let's get rid of that. This area up here is basically a desert, even though you don't think of it as a desert, but it's too cold for anything to grow, and no rain, only snow. So the annual average temperature matters. Also the range of temperature matters. If we look at California, we don't have a huge temperature range from summer to winter. Versus in Minnesota, it gets up to 90 in the summer, but then down to -40 in the winter. So there's a huge range of temperatures, and plant life has to be able to succeed under those conditions. So that has an impact on what kind of plant life can grow. We also need to think about the daily range of temperature. And that's what the word diurnal means. It means daily. The word diurnal we use a lot, so you want to get used to that. Let me see if I can write on this. No, that's not very happy. We'll write that down later. Diurnal means the day to night temperature range. So it's all very well if daytime temperatures are above freezing, but if nighttime temperatures fall to below freezing, plant life tends to die. So that will have an impact on the kind of vegetation that can grow in an area. Precipitation, if it doesn't rain, it's going to be hard to get anything to grow. Precipitation amount and distribution, and also the amount of cloudiness. Cloudiness affects insolation, not insulation, insolation. So there are parts of the planet where it's cloudy all the time, and therefore you're going to get less direct sunlight, and that's going to have an impact on the biome. So you might want to take a few minutes to have a look at this figure, get yourself acquainted with the distributions of some of the types of biomes that exist. A couple more things. We've been talking about a biosphere, so a question might arise, who cares? And I've put that more tactfully by saying, how does the biosphere affect climate or weather? And here we're only focusing on the terrestrial biosphere. So I can come up with 3 examples, well, mostly because they're in the book, but anyway, 3 examples of how the terrestrial biosphere impacts our climate. One is through impacts on the hydrological cycle. Okay, on a hot day, you've got sunlight pouring in, and to cool themselves off, the plants will transpire by evaporating water from their leaves, and the net effect is something that we call evapotranspiration. There's a word that you should get used to in case you don't already know what it is. As a matter of fact, I looked this up on Wikipedia, and here is a diagram that kind of explains everything. This is a slab of land, and you want to imagine that it has rained on this land, and now it's a hot day. The water on the ground is going to evaporate directly into the air, but there's also this transpiration process whereby water works its way through the roots of trees and through the roots of plants and then out through the holes in the leaves of the plants, and that's the transpiration process. And when we put it all together, we call that net thing evapotranspiration. Okay? And one of the things we know that happens during the process of evaporation is that you get cooling of air. If you don't know that already, don't worry, you soon will, and hopefully you'll understand why. So when there's evaporation, the air cools down more than it would have done, and right there's a local impact on your weather. Okay? If you live in an area that's sandy, you won't get that impact. But if you live in an area with a lot of cultivation, with fields, with irrigation and so on and so forth, you'll get a local cooling effect on hot days in summer. And if in your future you're a forecaster, that's something that you're going to have to pay attention to. Whoops. Okay, here we go. The other thing you get, of course, is reduced heating of the soil. Okay? And lost myself. No, I don't want that. Do I want that? No, I want this. When evapotranspiration is going on, some of the incoming sunlight is being used to evaporate the water, which means that less of that sunlight is going into the ground to heat up the ground. So that's another cooling impact. Secondly, there's an impact on albedo. Albedo is another term that either you should know or soon will be familiar. Albedo refers to the fraction of incoming sunlight that gets reflected back to space. Quick diagram time. Let's just get rid of this wonderful diagram. Nope. So if you have the ground like this, and in comes some sunlight, at least a portion of it is going to get reflected. And actually it can get reflected by clouds and so on and so forth on the way down. the amount that's reflected is referred to as the albedo. So the albedo will change depending on what the ground cover looks like. Okay, if this is bright sand, it'll be high albedo. If it's dark trees and leaves, it'll be low albedo. Okay, so the terrestrial biosphere impacts the albedo and therefore impacts how much radiation gets reflected back out into space. And then the last thing is an impact on what we call surface roughness. Roughness we care about if we are interested in predicting wind speeds, which, guess what, we are interested in predicting wind speeds. Let's have another quick diagram here. Suppose you have a surface which is very smooth, okay, versus a surface which is rougher and maybe even has a few rocks and boulders and bushes and trees and shrubs and so on and so forth. Okay, the winds many feet above the surface are unimpacted by what's going on at the surface, but down low the winds have at least the potential to be impacted by the surface. So on the case on the left here, where the surface is very smooth, the low level winds are not impacted very much by the roughness of the surface. In this other case though, where you have a rough surface, then I think it's easy to imagine that the low level winds are very turbulent, for example, and there's a lot of distortion of the winds by the roughness, not just near the ground but even higher up. So that's going to have an impact on how windy is it downstream of here. Case on the left would be much easier to forecast wind speed and direction than it would for the case on the right here. So the terrestrial biosphere impacts the surface roughness. Winds are slowed by rough land, and as my amazing diagram shows, you can think about two contrasting cases yourselves.